Okay, so let me start. By the way, someone turn on your microphone maybe. So please turn off your microphone before starting. So okay, so this is the second weeks of this lecture. So there might be new students. So welcome. So if you're first time to attend, please watch our previous videos in our YouTube website. Okay, so let's start today. So before starting, let's review what we have done so far. So okay. Yeah, start from here. So in this week, we've talked about the regression problem, right? So people introducing the regression problem, we compared what regression is and what classification is, right? So here are some examples from the single image, something like this one. We would like to estimate the depth information that is the continuous variable or the semantic segmentation value or the semantic segmentation label in a categorical variable. So this is the two kinds of the well-known problem in computer vision field. So in this week, we will focus on the regression problem, something like this one. And the next week, we will start to understand the classification problem to solve this kind of problem. Okay, so before keep going, I would like to show you some video like this. So this is the examples of the depth estimation and semantic segmentation estimation. So as you can see here, this is the images from the self-driving car. So from this single image, we can extract the depth information here and segmentation result in the bottom figure. So as you can see here, this depth information defined in the continuous space, maybe the real value, and this segmentation result defined in categorical variable or the categorical input. So this is some video demo. So by using this kind of information, yeah, we can reconstruct a scene, something like this. So as you can see here, this part represents the 3D information or the 3D structure information of this self-driving car, and this color represent this semantic category label, something like this. So by using this depth information and semantic segmentation information, we can reconstruct the 3D real 3D space with the semantic label, something like this. Yeah, another example is here. So yeah, so as you can see here, by using the depth information, we can reconstruct a real 3D indoor scene like this one. And yeah, this is the 3D mesh information. Actually, it's kind of the it's a form of the representation for 3D information. So like this one. So there's that. Yeah, here. So by using both depth information and semantic segmentation information, we can reconstruct a 3D semantic map like this one. So in this case, this indoor reconstruction scenario. Anyway, so let's go back to our lecture. Okay, so this is the kind of the regression and classification problem. So today let's focus on the regression problem first. So we discussed the very simple example, house pricing, right? Using the machine learning technique. So what's the regression? So regression is to relate the input variable to the output variable to either predict the output for the new input or understand the effect of the input on the output space, something like this. So as you can see here, this is the input variable and this is output variable, and each point represents the training sample, right? So in regression problem, we want to find out the mapping function between the input variable, output variable, right? So the data set for the regression can be represented as follows. So it consists of the pairs of the input and output variable. So input variable can be represented in a vector form like this one. So in this case, this is the large D dimensional feature vector, and what output is some kinds of scalar value or the continuous scalar value, right? So in here, large N represent the data set size or the training data set size, and D represent the dimensionality of our training input, right? So in machine learning, the input variable are also known as a feature or the some kinds of the variable, something like that, and output variables are known as the target, label, response, outcome, something like this. So there were two kinds of the goal of the regression, right? So first one is the prediction, and second one is the interpretation, right? So in prediction, we wish to predict the output for the new input vector. For example, what is the weight of the person who is the 170 centimeter tall, but something like that. And in interpretation, we want to understand the impact of the input on output. Here was some kind of example. And to solve the problem with the regression method or the regression machine learning technique, we have to define the mapping function first, right? So it was the mapping. It was the general form of the mapping function. So yeah, here's the thing. So first of all, we start with the very simple version of the linear regression problem, right? So what is the linear regression? So in linear regression problem, we want to find out the linear relationship between input and output. So what is a linear relationship? Linear relationship means something like the straight line in one case. So for example, let's say the yn is the output and xn is the input. Then we want to find out the mapping function as a straight line, having the W0 and W1 as a random parameter. So this is kind of the simple linear regression mapping function. And by adding the more terms, we can also extend this simple linear regression to something like this one, right? But if we introduce another nonlinear term, something like the x1 times x2 or the x2 squared or something like that, it's not a linear regression anymore. It's like it will be the nonlinear regression term. So here, so you can understand this mapping function. So in here, W0 is the cross section between this straight line with the y-axis, and the W1 represents some slope of this straight line, right? So the goal of the simple linear regression is to find out this straight line. Precisely speaking, we have to find out this straight line, okay, that approximate this training data set we have. Okay, so in other words, given the data, we would like to find the optimal parameter W here, right? So this is called the learning the parameter or the estimating the parameter or the fitting the model. Okay, so to do so, we need optimization algorithm. Actually, today we will focus on this optimization part, but before starting, we need some kinds of the terminology, just called the cost function. Okay, here's the thing. So, okay, let's think about a very simple example. When there is a two training sample, so x1 is 0, y1 is 0, and x2 is 2, and y2 is 1. So this is very simple example. Then we want to find out the straight line that approximates this training data well. So there are infinitely many kinds of the possibility among the W0 and W1, right? So when we use the W0 as a 1.5 and W1 as 0, the straight line looks like this, right? When W0 is equal to 0 and W1 is equal to 0.5, the straight line is going to be like that, right? This is another example, right? So as you can see here, which one is best? Middle one, right? Why? Because the distance or error between the straight line and training data is the smallest when we define when we choose the W0 as 0 and W1 is the 0.5, right? But actually it's not a efficient way, right? So we cannot search the whole possible W0 and W1, so we need more systemic way. So it's a brute force, right? So I searched this brute force in Korean. So it's like, what's that? 무작위 테이프. Yeah, like so. Actually, it's not an optimal way, right? So first of all, we have to define the cost function, right? So what is the cost function? So cost function means the aggregated distance between the ground truth data, ground truth value, and estimated value, right? So we can define this distance as a en or something like that. And the cost function means to measure or to measure the distance between the ground truth one and estimated one, right? So this is called the cost function, and the optimization is to find out the optimal parameter W that minimize this cost function. Okay. So the formally the cost function or energy function or the loss function or the training objective is used to learn the parameter W that explain the data well. So those cost function quantifies how well our model explains the data, or in other words, how costly our mistakes are. So this is the definition. So last week we also discussed some simple examples to find out the optimal parameter W, right? So it was a simple case. When we just considering the W1 only, like this. So when we plot the cost function or cost curve with respect to the W1 as a parameter, so the cost function looks like, right? When you consider the L2 norm, right? So in here, we can say that the optimal parameter W1 should be 1 here, right? Because it makes the cost the minimum, right? So if we think about a little bit more complicated case here, W0 and W1 case, we can also do similar things. So this is the training data set, and this is the estimated mapping function, and we can draw some loss function with respect to the W0 and W1. It looks something like this, right? It is defined in the 3D space here, but it is hard to draw this 3D loss function every time. So we need to do more efficient way to draw this one. So we use the contour plot. Looks like this. So this is the 2D representation of this 3D surface model. So from this one, we can search the optimal parameter space like the W0 and W1, something like this, right? So by search the possible W0 and W1, we can measure the errors, right? Then we can say that, and at this point, we can minimize the error between the ground truth and estimated mapping function, right? So this is the optimization, one of the optimization technique, right? So, and there was the two kinds of the cost function, right? Mean scale error and mean absolute error. So when we draw this one, first of all, let's define the error between estimated values and ground value, something like this. Then we can draw this MSA cost function with respect to the error rate. Error values, something like this one, and MSE this one. It shape looks like this, right? Why? Because this part is the yeah. So it's just like the scale function, right? 2D let's say polynomial curve, right? And when you think about the mean absolute error, we can draw the similar cost function, something like this, something like this, right? This is the these two kinds of the cost functions are one of the most popularly used cost function. And there was the two desirable property of the cost function, right? One was the symmetry around the zero, looks like this, right? And another desirable property was that the large mistake and very large mistake should be penalized similarly or equally. So, for example, this straight shape is not a good mapping function. So it's not a okay, let's yeah, it's not desirable. This straight line is desirable. So good cost function can guarantee this straight line rather than this one. Okay, so this is two kinds of the desirable property. And there was the trade-off between the statistical properties and computational trade-off, right? So you can think about this one. Okay, so let's start today's topics. Actually, our previous examples was the grid search, right? Grid search. So we compute the cost over whole values W in a grid and pick the best, right? But it was the brute force and extremely and it has too many product, resulting in the exponential computational complexity. So we need a more systemical way to optimize this parameter. So this is today's lecture, today's topic. Okay. So before keep going, do you have any questions so far? Wait. Yeah. So I'll show you some. here. So as you can see here, max loss of W with respect to W means the maximum values, and the argmax of the loss function with respect to W means the index that maximize the loss function. So in this case, this one is 3 and this one is 5. Okay. What's that? Can you tell me the answer for those 3 examples? Yeah. Actually, frankly speaking, it's really hard to classify which one is a prediction problem, which one is an interpretation problem, right? It's not a different thing, but it's closely related, right? So in my opinion, the first one is the prediction problem, and second one is interpretation problem, right? Third one is prediction, right? So we want to predict the life expectancy with respect to the number of packs, right? And the first one is also prediction, right? And last one is also what? Last one is also prediction, right? But it's also interpretation, right? Because we would like to understand the tendency between the number of birds and what is that? Number of years from now, right? Is it correct? Right. So actually, it's not hard to classify this one into the prediction or interpretation. Okay. So let's continue. Okay, so let's continue. So we want to find out the more systemic way to find out this parameter W, right? Then how can we do that? So let's think about this figure first. So let's imagine you are at the mountain and you want to go down to the go down to the city in the mountain, right? Then which one is the most which direction is the most efficient way to go down the mountain? Which direction is the most important most efficient way? Of course, the following the path is one of the most safest way, but let's just think about the most efficient way. What is the most efficient way? So one of the most efficient way is to, right, you're right. So following the steepest way, right? So as you can see here, let's imagine you are here now. So you can go the 360 to say the direction, something like this one, or this one, right? Something like this. In this case, you can choose the direction, right? You can choose the direction to go down the mountain, right? So which direction is the most efficient way? Maybe this one, right? Why? Why? So when we follow this direction, we have to follow the something like path, right? But if we just the steepest direction, it will be something like this. So it would be much faster than the other direction. So this is the main idea of the gradient descent algorithm. So what is the gradient? What is the gradient? 최선묵 학생인가요? 수학과네요. So I would like some question to you. So what is the gradient in mathematical department? Okay, so derivate, right, similar, but actually the gradient is the slope of the tangent to the function. So here is the answer. Here's the answer. Then what is the tangent? What is the tangent to the function? What is the tangent to the function? So we can draw the very simple example here. So okay, let's think about the 1D case. So let's say we have a function looks like this, right? Let's say we are here. Then the gradient means the derivation of this. Okay, let's draw something like this. X, let's say this is x1, right? So gradient means the how to say something like this one. So we can say that the gradient it's like the delta x and delta fx. So ratio between function difference and variable difference, something like this. So this is a very simple notation of the gradient. So it can be represent something like this. So this x and x first x, something like this, right? So in this case, this line represents some tangent function, one tangent to straight line at this point, right? So this is the definition of the gradient. So in this case, at this point, we can go this way to minimize this function, right? I mean, this way is much faster way than this way, right? So it means that so the gradient is the slope of the tangent to the function. So it points to the direction of the largest increase of function. So in other words, to go down the mountain or to go down the loss function or to go down the let's say our loss function, we have to go negative gradient direction, something like this one, right? So in this case, the gradient at this point will be looks like this way. So we have to choose this way to minimize this one, right? So this is the main idea of the gradient descent. Okay, so yeah, so here's the idea. So then how can you do that? So anyway, we have to start from the initial value, right? So let's say this is the initial parameter, right? For example, W1 is equal to 0, or W1 is equal to 1, something like this. And we can start from the random initial parameter, right? And then we can go we can go the direction to keep changing this parameter to reduce our loss function, right? Until we hopefully end up the minimum. So this is the basic idea of the gradient descent. Okay, let's see the visualization. So we have a cost function. Cost curve looks like this, right? This cost curve is defined with respect to the W0 and W1, right? So this is the cost function L of W0 and W1, right? And let's say we start from here, initial state, right? So there will be the there is going to be the three kinds of question. The first one is the where do you start, right? The first one is the where do you start, and second one is the which direction do we have to follow, right? Which direction, right? The third one is the how much do we move, right? So these three kinds of question can define this gradient descent algorithm, right? So in other words, the first question is related to the initialization of our parameter of the model, right? For example, something like the W0 and W1, right? And the second question is related to the gradient, right? So if you remember the gradient, it's like the direction. It determines the direction, right? So precisely speaking, it should be negative gradient direction, right? So it related to direction. And last question is how much move is related to learning rate. Okay, so as you can see here, let's say we start from here. Yeah, this is the initial state, and in here we can search the possible direction, something like this, right? Then we can say that this direction is the optimal direction. In other words, this direction is the negative gradient direction, right? So we can move to this one, this way, right? And then how much? It depends on the learning rate. We will see this one later in the next slide, but this learning rate determines the speed of this movement, or the magnitude of this movement, or the step size of this movement. And from this one, it will be the new state or the new parameter of the model. And then we can do the same things from here, right? Then by iterating this procedure like this, we can converge it to our minimum among the whole possible parameter candidate. So this is the gradient descent algorithm. Okay, so there might be a question. What about start from the different initial state? Let's think about something like this. So it was the previous initial state, right? So the path was something like this one, right? But if we start from here, it means that if we start from the different initial state, then our optimization procedure or our optimization direction will be changed, right? So because if we start from here, the direction will be changed, look like this. when we compare to this direction, at this point, the optimal direction might be looks like this, right? So if we start from the different initial state, we can follow the different path to minimize this loss function. So it will be something like this. So what does it mean? So what is the difference between these two paths? Let's say we have the same learning rate and same iteration, but we converge to the different point, right? The first case converges to the here, the second case converges to here, right? Because we just start from the different initial state, but we converge to the different minimum point, right? So in other words, initialization. Oh, sorry. Initialization of the our parameter of the model is really important to converge our loss function in our optimization process. Okay, so this initialization is one of the most important issues in the gradient descent or the optimization. Okay, so let's define the algorithm for this gradient descent as some equation, but main idea is exactly the same as this figure. Okay, so let's do that. So first of all, we have to start from some random initial parameter, something like the W0 or W1, right? Maybe here, right? Then we can use some iterative procedure by using some kind of for loop or the while loop, right? You know what it means, right? To iterate this each step, right? And because we already have the cost function W0 and W1, right? W1. Then to move this parameter W, we have to compute the gradient, right? So gradient, which can be written as W derivative W0, W1, right? So by using this gradient with some constant value here is called the learning rate, we can change the W0 values as a new W0 values. So this one is the previous parameter. Oh, sorry, previous parameter, and this one is the new parameter. Okay, so by using the gradient and some constant value, just called the learning rate, we can change this W0 values to reduce this loss function. Okay, so this is just one step in the gradient descent algorithm. Of course, because we have the two learnable parameter W0 and W1, we have to define the two kinds of the update equation. First one is for the W0, second is for the W1, right? So in this case, we first of all we have to compute the derivative of the loss function with respect to the W1, right? Or just the partial gradient of the loss function with respect to the W1, and by multiplying the alpha value or the learning rate, we can change the W1 values to the new W1 values. Okay? This whole stage just this part is just one step in the gradient descent algorithm, and by iterating this each step, we can finally get the optimal W0 and W1, which may make our cost function as a minimum. Okay, so it might be the optimal value, optimal parameter. Okay, so let's compare this one to our previous example. So if you remember our previous way, something like this one, by searching the whole possible candidate in gradient descent, we need we just require to compute the few point value, something like this one, right? So it will be much faster and much efficient than the grid search algorithm, right? So this is the gradient descent algorithm. So actually, the most of the deep learning methods are based on this gradient descent algorithm, which will be discussed after maybe 3 weeks or 4 weeks. But this gradient descent algorithm is the heart of the deep learning optimization. Okay. Okay. So, do you have any questions so far? No. Then let's keep continue. So, okay. So, how can we compute the gradient? How can I compute the gradient? There are two kinds of methods. So, okay, so let's think about the very simple example. Let's say we have a mapping function, something like W0 plus W1x, right? Then let's say we have a cost function of the estimated one and ground truth one, which is defined something like this, right? Right? So in the function of W, right? So this is our loss function. Then how can we compute W? How can we compute the gradient of the loss function with respect to W? How can we compute this? Compute this one. There are two kinds of the way. So first of all, numerical gradient and analytic gradient. So first of all, in numerical gradient, in here, we can represent this one as a delta x and delta f, or it will be something like f x plus h minus fx, something like this, where h is going to 0, might be the very small value, small h, right? This is a way to compute the gradient using the numerical gradient method. So for example, in this case, we can compute the gradient. Maybe let's say h1 is 0.001. Then we can compute W as a 0.001 and H, let's say current W is W star plus 0.001 minus L W star, right? W star means current parameter, right? Current parameter, right? So we already know the this Y value and X value because they are training data set. So we can compute this one as our gradient, right? But as you can see here, it's not easy, right? It takes time to compute this one every time, right? So it means that it may be slow, or actually it's just approximation of the real gradient, right? So this is a limitation of the numerical gradient. So in most cases, we use the analytic gradient. So what is the analytic gradient? So analytic gradient means we can directly estimate the gradient this one as some kind of a derivation rule, right? So for example, in this case, we can compute the loss gradient with respect to the parameter W, something like, how can it do? 2 FWX minus W FWX, right? So in this case, FWX is the W0 plus W1X, right? So it's going to be 2 FWX, and what is that? Let's say if we consider the W0, it would be just 1, or when W0 case, and W1 case, it should be something like X value, right? So this kind of the derivation or this kind of computation is the analytic gradient. So it's an accurate gradient, and if we define this derivation, we can just compute our gradient by using this equation, right? It will be much faster than this numerical gradient, and it will be more accurate than the numerical gradient. So in most cases, we use the analytic gradient rather than using the numerical gradient. So from here, we will just use the analytic gradient to derive our optimization algorithm or our gradient descent algorithm, something like that. Okay. Okay. So is there any questions so far? I just guess most of you heard about the gradient and heard about numerical gradient and heard about the analytic gradient already, right? So am I right? Okay, so then let's continue. Okay, so let's think about this example. Okay, so we have this source function when fwx is equal to w0 plus w1x, right? And this loss function is defined something like w0 plus w1x minus y squared, right? Because this one is this one here, right? Then how this gradient descent move to the okay, so this gradient descent direction is dependent on the sign of the gradient number. So for example, okay, so let's say we have a cost function, looks like this one. Looks like this one. Okay. So first of all, let's just consider W1 without considering the W0. So in this case, this is kind of the partial gradient. So partial gradient means we just consider the W1. So in this case, W0 is going to be the just constant value when we compute the gradient with respect to the W1, right? So in this case, let's just remove this part to understand this one. So, okay, let's say we are here, right? So we are here. Then what is the sign of the gradient at this point? What is the sign of the gradient of this point? 여기가 지금 설명이 좀 복잡해서 제가 한국말로 한 번 더 설명할게요. 그래서 지금 이 페이지를 보시면 되는데, 그러니까 우리가 어쨌든 로스 펑션이 있고, 로스 펑션을 W로 미분한 그레디언트 값을 이제 알아야 되는 거죠. 우리가 이제 그레디언트 디센트를 풀려면. 근데 이제 사실 그레디언트라는 자체를 정의를 내리면은 사실 우리가 이제 뭐 고등학교 때 배웠던 걸 잘 떠올려 보면 우리가 어떤 그레디언트를 계산한다는 거는 어떤 룰에 의해서 지금 보시면은 이렇게 그레디언트를 계산하는 룰에 의해서 계산할 수도 있지만 실제 이 룰을 만들기까지는 원래는 사실 이런 펑션을 따랐던 거죠. 그렇죠? 그래서 fx 플러스 h 마이너스 fx를 h로 나눈 값을 h를 매우 작게 하면은 h를 매우 작게 하다 보면 사실 우리가 어떤 룰에 의해서 계산한 그레디언트 값이 같아진다. 사실 그렇게 생각할 수가 있던 거고, 그 말은 사실 우리가 어떤 임의의 작은 h 값을 골라서 그 h 값을 가지고 이렇게 그레디언트를 계산을 하면 정확하진 않지만 우리가 어떤 애널리틱 그레디언트의 어프로키메이션으로 사실 생각할 수가 있다는 거죠. 그래서 사실 우리가 실제 펑션 알고 있고 h 값 알고 있고 x 값 알고 있고 그러면 사실 우리가 이걸 그냥 계산하는 거죠. 그러니까 그 어떤 W 스타라는 현재 포인트마다 저 값을 이렇게 다 계산할 수 있는데 사실 그러면 사실 생각하는 것처럼 느리고 어쨌든 어프로키메이션이기 때문에 정확하지가 않은 거고, 그렇기 때문에 우리가 이제 그레디언트 계산할 때는 어떤 이런 뉴머리컬 그레디언트 기법보다는 실제 이 펑션 자체를 우리가 어떤 미분 룰에 의해서 실제 계산을 해서 이거를 사실 쓰는 거죠. 이 계산으로 정의된 미분 이퀘이션을 가지고 우리가 이제 그레디언트 계산을 하는 거죠. 그럼 이제 훨씬 더 빠르고 훨씬 더 정확하게 계산할 수가 있는 거고, 이제 사실 이건 설명을 위했던 페이지였고, 앞으로 이제 우리가 이 그레디언트 디센트를 계산할 때는 기본적으로 애널리틱 그레디언트를 사용한다 라고 이제 생각을 하시면 돼요. 그 말은 뭐냐면 우리가 어떠한 로스 펑션 또는 어떠한 펑션을 가지고 있을 때 그 펑션을 우리가 원하고자 하는 예를 들어 W라고 하면 W에 관해서 미분이 될 수 있는가, 첫 번째 미분이 될 수 있는가, 그 다음에 두 번째 미분을 어떻게 되는가, 미분값이 어떻게 되는가를 알아야 되는 거죠. 이 두 가지를. 그래서 앞으로 이제 우리가 그레디언트 디센트를 계속 하다 보면 어떠한 펑션이 어떤 우리가 네트워크 파라미터 또는 어떤 머신 러닝 파라미터에 관해서 어떻게 미분이 되는가에 대한 수식을 계속 이제 우리가 뭐라고 하죠? 이거를 계속 딜라이브를 해야 되는 이제 과정들이 계속 나올 거예요. 그렇기 때문에 이제 이 미분을 알아야 되는 거고, 일단 저의 가정은 우리 이제 여기 들어온 우리 여러분들은 미분에 대해서 일단 기본적으로 다 알고 있다고 가정을 하고 있었고, 사실 이게 조금 이제 어려우신 분들은 좀 간단한 미분에 대해서 공부를 하고 올 필요성이 있는 것 같아요. 근데 뭐 어려운 걸 할 필요는 없고 그냥 정말 간단한 미분 룰. 그러니까 예를 들어서 뭐 스퀘어가 어떻게 미분되면 어떻게 바뀌느냐, 이 정도는 사실 저희가 알고 있어야 이제 그 다음을 따라가는데 도움이 될 거라고 생각을 합니다. Okay, so okay, so let's continue. Okay, so let's say if we are here, let's say this is the current point, right? This is current point. Then the gradient at this point will be the positive value, right? With the positive value, right? Because the tangent line at this point will be something like this. The slope of this line, the slope of this line, the slope with the sign of this slope will be the positive value, right? So in this case, this W1 is the current value. Then we can move to this W1 value to the where? To the negative direction, right? Because if you remember our previous one here, this part, we have to move our parameter W to the negative direction of the gradient, right? So if you remember this one, this equation make this current W1 to the negative point, negative direction, right? So it means that this point move to this direction, something like this. Okay. What about the negative number? What about the negative? The sign of gradient was the negative. It means that let's say we are here, right? Let's say we are here. The W1 was negative, right? Because the tangent line here, right? Tangent line here, and this sign of this slope is the negative value, right? So in this case, this W1 move to the positive direction, right? Positive direction. So it will be something like this one, right? Positive direction. So from here, we can understand that the direction of the movement, direction of the one-step movement is dependent on the sign of the gradient value. Okay. And another thing is that the learning rate, if you remember this one, this constant value was called the learning rate. Actually, this learning rate is just a constant value. For example, alpha is something like the 0.01 or alpha is something like the 0.0001, blah, 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 something like that. This is just constant value. Then what happens if we adjust this alpha value when using the gradient descent algorithm? Here is the example. Okay, let's say this kind of cost function here and here. Okay, and then let's say we start from here, right? And if you remember the previous slide, in here we have to move this direction, right? But how much? It depends on the learning rate. So if the alpha is too small, this step is moved very slowly, something like this. This is called the learning rate, right? So the gradient descent will be very slow if we use the too small alpha value. Then what about we use the too large alpha value? Then in here it might move to this this direction, right? If we use a too large alpha value, then what happened? Then what happened? The next step should be start from here, right? Then in here, the next step move to the positive direction, but with very large alpha value, it will be something like this, right? And next step will be something like this or something like this. So it might be diverge, not a conversion, not a convergence, because our goal is to align here, right? Our goal or the goal of the linear regression. But if we use the too small or the too large learning rate, it might be very slow, or the might be diverge, not convergence. So, in other words, it may fail to converge or even diverge. So, in here, we can say that proper learning rate, proper learning rate is really important to to find the optimal parameter W when using the gradient descent. So the question is how to fix the optimal or the proper learning rate. We will answer this question in next lecture. Okay. Anyway, the choosing the optimal learning rate is one of the most important issues in the gradient descent algorithm. Okay, then what is the limitation of the gradient descent? Actually, there are many limitations of the gradient descent, but I want to show you, or I want to emphasize the one thing. So far we just considering such a nice cost function, right? Such a nice cost function. Actually, in fact, in real case, it's really hard to find such a cost function. I mean, the most of the cost function looks like this. This is called the non-convex function, non-convex one. So if you remember this one, actually it's not a convex one. So there might be some curve on the surface, right? So in most cases, the cost curve or the loss function looks like this, right? So in this case, if we start from here, right, then we can move to something like this one, right? Then what if we start from here? What if we start from here? What is the gradient at this point? What is gradient at this point? So if you remember the definition of the gradient, it was the slope of tangent line, right? Slope of the tangent line. Then in this case, what is that? 0, right? 0, right? So it means that the loss gradient with respect to the W1 will be 0 at this point, right? At this point. Then what happened? What happened? If we are here, we cannot move to any direction. Why? Because this term will be 0. Then this W1 remain fixed because there is no movement of positive direction or negative direction. So you remain fixed, right? So it means that actual our global minimum not here, global minimum, and let's say this is the local minimum. Local minimum. But in this case, if we are here, we cannot go the global minimum, right? Because there is no gradient anymore here. So that's why if we use the gradient descent, we frequently get stuck to the local minimum. So this is the one limitation. What about we are here? We are here. What about we are here? To move to the global minimum, we have to move this direction, right? But at this point, the gradient, the slope of tangent looks like this, right? So this one move to this way, not this way, right? So in this case, we cannot we cannot convert to the global minimum if we just use the vanilla gradient descent algorithm, right? So to solve this kind of a limitation, there were so many variants of the gradient descent algorithm. So in deep learning, how to say, in deep learning world, most of the optimization method based on the gradient descent algorithm, but they never use the gradient descent algorithm directly. They use some kinds of the variant to improve this kind of limitation. So we will discuss this one later, but in here, please remember the gradient descent algorithm have some kind of limitation itself. Okay, so this is the limitation of the gradient descent algorithm. Okay, so so far we've talked about what is the linear regression and what is the regression problem, and how can we define the mapping function for the regression problem, and how can we define the cost function and minimize this cost function, right? And right, what else? What else? So far, we just considering the single input and single output, or one-dimensional input and one-dimensional output. For example, when you think about the house pricing problem, the input was something like this one, and output was something like this one. So input was just the real value, just the one-dimensional real value. Output was also one-dimensional real value, right? Then, is it correct? So the price of the house is only depends on the size of the house, correct? No, right? Because the household price also depend on so many other factors, something like the number of bathroom or the number of floor or the age of house, something like this. So the final house price is depend on the several kinds of the feature. So let's say this kind of things is feature, or 특징 in Korean, 특징 or feature. So in most machine learning case, we have to consider the multiple feature case, not a single feature case, because the most problem can be formulated with a multi-variable or the multi-feature input with a single output or single dimensional output. So in this case, we can say that nth training sample, nth training xn will be the vector form, something like this one, and output is still single value. So for example, x1, this sample will be the vector form, consisting of something like this one, right? Yeah, right. And y1 is 460. Now we can consider the multivariable case or multivariable training data set, but if we can consider this kind of the multivariable case, the cost function and optimization are almost exactly the same. So if you fully understand our previous topics, you can easily extend those one to the multivariable cases. Okay. So in this case, this one is called the first element of feature xn, something like this. Okay? Something like this. And okay, so let's do similar thing. The similar linear regression serving using this multivariable case. Okay, so if you remember our previous mapping function, define something like this, consists of W0 and W1 and X1, then we can extend this one as like this, right? Unlike the previous one, we add 3 more input variable, 3 more input feature, something like that. So for example, like this. So comparing to our previous simple linear regression mapping function, like this, by using this one, we can improve the accuracy in the linear regression in the linear regression problem. So for example, the new mapping function for the multiple variable cases will be something like this, right? So, and in generally, for convenience of the notation, we just define, here's a mistake, x0. We just assume that x0 is going to be 1, right? So, in this case, the input feature vector will be looks like this in the large T plus 1 space, and the parameter space is also R large T plus 1 space, right? Then using this vector notation, we can represent this mapping function looks like this, right? So this is just the dot product, right? The product, and it will be something like x and 0, x and t, like this, right? So this is just the product, right? So in this case, if we use this kind of the mapping function, we can say that this is the multivariate linear regression problem. Not a single linear regression problem anymore. It will be the multivariable linear regression problem, right? So we can do the same things. We have a mapping function now. And we have a learner parameter. Rather than v0 and v1, we have a large T plus 1 variable, right? And we can similarly define the cost function here. So in this case, it will be something like W transpose times X minus YN square, right? This is a multivariable linear regression case. And what about gradient descent? If you remember the single variable case, the gradient descent looks like this, right? You remember this one? It was the learning rate and the gradient here. In multiple variable case, we can do similar thing. But here is the difference. So for each variable, if I is, when I is 1 to the t, right? No, 0 to d, right? Because this is our target parameter, right? So we have to compute each step with this equation, right? So if you consider this equation, then we can compute this gradient in the using the analytic gradient, right? Then how can we compute this one? How can we compute this analytic gradient? Analytic gradient will be something like this, right? Why? Because this term is consisting of W0, X0 plus W1, X1, blah, 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 WT, XT, something like that, right? So if we compute the derivation of this term, it will be XNI. So this is a new one-step equation in multivariable cases, right? So this is a gradient descent for the multiple variable cases. Okay, so in this week we will talk about the linear regression problem, right? So we derived what cost function is and what the gradient descent algorithm means, right? Then it's just done, right? Then in next week we will talk about the classification problem or logistic regression problem by using the similar terminology like the cost function and the optimization algorithm. Okay. Okay. So this is the end of today's lecture. Thank you for listening. So if you have a question, please let me know. Thank you. Okay, so the first question is for the multivariate case, there are 3 procedures. We just write the 3 cases. It's not a 3 procedure. Yeah, it's an equivalent procedure because okay, how can I? Yes. Yeah, these 3 kinds of the procedure are equivalent, right? I just rewrite this each statement, okay? And what is the second question? Analytic gradient again. Okay, so okay, let's go back to here, right? You wanna know the how to compute the analytic gradient or the difference between the numerical gradient and analytic gradient? What do you want to know? How to compute it? Okay, to understand this procedure, you need some kind of the mathematical background related to the derivation rule. Okay, so to understand this part, please search the derivative rule or chain rule. Please Google these 2 terminology to understand this one. Actually, it is really hard to answer to explain all of everything. So please understand. Is there any other question so far? 1x. 요거는 그러니까 W0에 대해서 미분을 계산할 때는 요게 그러니까 F를 W로 미분한 거는 1이 되는 거죠. 그쵸? 왜냐면 여기서는 W0에 대한 텀은 하나밖에 없으니까. 근데 이제 W1에 대해서 미분할 때는 요 텀이 X가 된다는 소리죠. 왜냐? 이 부분에 X가 남아있으니까. 답변이 됐나요? 네. 이게 좀, 이 아이패드가 잘 안 써지네. 네. 네. 다음부터 좀 더 잘 그려보겠습니다. Okay, so is there any other question?